Okay. So is it all good now? All good? ኤልያስ ኦኬ ነው አሁን ይሰማችኋል? ምንም ፊድባክ እያገኘው ስላልሆነ እርግጠኛ አይደለሁም መጀመር ካለብኝ።
Sure, volume should.
የእናንተ ይሰማኛል አይደል? የኔ ከተሰማችሁ አላውቅም። ኦኬ ይሰማችኋል?
ይሰማል።
ኦኬ ስለዚህ ሌሎቻችሁ ማይካችሁን ሚውት አድርጉ። ክብሩ ያንተ ነው ክላስ ያለው?
እሺ
ይሰማል ዶክተር?
ይሰማኛል። ግን አሁን ኤልያስ ጆይን አድርገሃል። እንደገና የክብሩም ኦን ነው የሁለታችሁም። ስለዚህ አንዳችሁ ሚውት አድርጉት። ኦኬ አሁን ይሻላል። ስለዚህ የኤልያስ አሁን ይታየኛል። ሌሎቻችሁ አይ ቲንክ ኦኬ ነው።
አሁን ይሰማል?
ይሰማል። ስለዚህ ሚውት ላድርግህ አንተንም።
አዎ
ቀድሞ ጥያቄ ምናምን ከሌላችሁ ቀጥታ መጀመር የምንችል ከሆነ ሚውት ላድርገውና ያንተን፣ ከዛ በኋላ ፎን ማድረግ ትችላላችሁ ትፈልጉ። Okay. Thanks for your patience everyone. ስለዚህ እንዳላችሁት ባለፈው ለዛሬ ሪቪዥን ነው የማደርገው። ያው ብዙም አዲስ ነገር አላነሳም፣ ግን ምናልባት ከዚህ ኮርስ ብትማሩ የሆነ ወይ ደግሞ ማወቅ ያለባችሁ ነገር ምንድን ነው የሚለውን ነው ዲስከስ የምናደርገው። እንደገናም ደግሞ ያው በዚህ አጋጣሚ ጥያቄ ምንም ካላችሁ ሆፕፉሊ ዲስከስ ማድረግ እንችላለን አንዳንድ ነገሮችን። ስለዚህ ያም ጥሩ ኦፖርቹኒቲ ይመስለኛል። Okay, so as you all know, this unit is mainly concerned with mineral processing. So what I want you to know when we say mineral processing is only part of the processes that we involve to extract metals, for example. So it's not the complete process, but it's only half of the process, let's say, because typically mineral processing is concerned with upgrading or beneficiation. Okay, it's not necessarily about extracting the value. So when I say the value, for example, we're not really at the stage of extracting gold or copper or iron at this stage. So we're only upgrading the ore. Okay, so that's the whole purpose of mineral processing. So why do we upgrade the ore? Because we know, for example, if it's a gold ore, any given maybe high grade ore for gold has 10 grams of gold in a ton. Okay, so it's not a lot. It's like 10 parts per million. So obviously the vast majority of whatever we dig from the ground, even for a high grade ore, is basically waste. So in mineral processing, the whole point is instead of putting all these materials through the processing mill and try to extract the gold out at the end of the process, what we're trying to do in mineral processing is to recover only the part or the portion that is valuable. So when I say valuable, maybe the gold is distributed in 2% of the rock. And typically that 2% might be, for example, a sulfide. So we have 2% sulfide in the whole ore, and that 2% sulfide mineral is the one containing the gold. So ideally in mineral processing, the whole point is let's just recover the 2%. In this case, maybe sulfide or an oxide. Why? Because we know the majority of the gold is found in that 2%. So we want to grow from the whole bulk material to a portion that has most of our gold, and this portion might be 2%. So if you start with 100 ton starting material, maybe the vast majority of my gold is in the 2 ton from the 100 ton. So this kind of separation of the valuable from the waste is done at the mineral processing stage. Okay, so what happens next? What happens next is we take that 2%, which is called a concentrate, and then we can do chemical processing using leaching or hydrometallurgy, or we can use pyrometallurgical processing, where we basically use smelting. So we're not talking about smelting and pyrometallurgy in this particular course, but those are the stages that follow from mineral processing. Okay, so in general, to achieve a good success in mineral processing, you need to do sizing, you need to do comminution, and you need to do separation. And those are the main stages that are involved in mineral processing. And for this particular course, for the first part, the one that we did this semester, we were only focusing on the comminution part and the sizing part. So once you do comminution and sizing, then hopefully in the second semester, you can then take this material and do maybe use gravity method or flotation or any other method to upgrade the ore even further. So both this semester and next semester mineral processing are still dealing with beneficiation. But obviously before we do detailed beneficiation, we need to do proper crushing, grinding, and sizing. Okay, so that's the whole point of mineral processing involves these stages, and I just want you to understand these as the main points in our discussion. So I showed you this slide where we said maybe some of you are from geology and maybe some of you are from mining, so you understand those initial stages. So obviously we have to first find the deposit. We have to look for it. And then once there's some feasible resource, we need to do some metallurgical work and actually confirm if that resource is available. So to confirm that, we need to know we have a good amount of tonnage. That's a large resource. And we need to know that the grade of that deposit is also economic to extract. So once we have done that, we have confirmed the resource, we have done metallurgical work, we know a rough process of extraction, then we can plan the mining stage where you could use open cut mine or you can use underground mine to bring the material to the surface. Okay. Then once you bring it to the surface, you would need to do typically crushing and grinding and separation. That is the beneficiation part. So that's the mineral processing part. And as I said, once you produce a concentrate from here, you do smelting or you leaching, and that follows into producing a high-grade material. So that's the general trend. So at least what I want you to do is just understand this process. Because when you say mineral processing, sometimes people think it starts from mining, even including mining, and all the way to refining and fabrication. Okay. But when you say mining, mining is mainly to do with bringing the ore from the ground. So that's the mining part. It's more to do with digging it up and bringing it to the surface. The processing part is what follows. Okay, so I want you to understand these differences. Okay, familiarize yourself. If you're not really familiar with those concepts, at least that's the process of thinking. So once we have this thinking in our head, then we can talk about the different stages. We can talk about how you optimize different stages. All those things can follow. But at least in our head, we need to have this nice flow of how material or resources are extracted from the ground. Okay. So obviously, I'm assuming in different parts of your course, you're going to deal with those different sections. Maybe you guys have already done your geology, your mining, you probably have some background there. But at least for the mineral processing part, we can go into details of what are the several stages involved, and we can talk about the extraction stages as well. Okay, so typically people talk about mining and metallurgy and geology. Okay, so there are three different stages, so three different areas, if you like. Geology is to do with finding the ore. Mining is to do with digging the ore, bring it up to the surface. And processing or metallurgy or extractive metallurgy is to do with extracting the valuable. Okay. Maybe you know all this, but I just want to make sure that you actually have this in your mind. Okay, so in mineral processing, then what is involved, as I said in the past, so probably once you bring everything to the surface, then So I say everything to the surface. There are some places in the world where they actually start beneficiation underground, for example. So as soon as you say, do your blasting before you actually carry everything to the surface or to the processing plant, there are actually some operations that can be done, like coarse gangue rejection, where you can get rid of some of the waste as soon as possible, or people do in situ leaching and all other processes. So obviously I'm not going to talk about those and complicate the issue, but at least once you do your mining, if you're going to process it, then you'll bring it to where the processing plant is, and that processing plant involves typically crushing and grinding. Now you can get away with mainly one crushing without doing any grinding. You can get away with just one stage of grinding with no crushing at all, okay? Or you might do several stages of crushing and several stages of grinding. So all this actually depends on the nature of the ore. So there's nothing that says you have to do crushing and grinding, or there's no rule that says you have to do 3 stages of crushing. It all depends on the nature of the material. Okay, so I need also you to understand this. So this, especially mineral processing, is actually very site specific. So there is nothing that you can say, oh, this is how it's done in this place, and I can adopt that directly. It doesn't work like that usually because of the variation in mineralogy. You have to have individual studies for individual sites, understand the ore to come up with your processing method. So that's why I say they can slightly vary. So crush and grind. Between the crushing and grinding, usually we put a screen as well to recycle back the oversize. And once you do grinding, we also do classifiers to recycle back the oversizes. Okay, so they're all operated in closed circuit. And this was the main focus of this particular course. Okay, so once you do classification after grinding, we do either direct extraction if they are low grade ores where there's no benefit in actually trying to upgrade them. So these are probably things to do with laterite ores, iron ores, and so on. Otherwise, we do beneficiation or concentration. As I mentioned, different properties of the ore can be exploited for that purpose. Okay, but at least again, just have that framework in your mind and understand what are the different stages and the different processes involved. So this is one of the processing plant, a picture of a processing plant that is not far from where I live. I think it's about maybe 20 kilometers away. And it is a very simple gold processing plant. Okay, so as you can see, I will try to use. So that's where the crusher is. They have a gyratory crusher somewhere there, and ore is carried and stockpiled. Okay, so this is stockpile, and from which the next step will be grinding. So those are the mills there, and then subsequently into processing. Some gold ores are called refractory. Some gold ores are called free milling. So again, depending on whether the ore is complex or easy to deal with, you can actually have different processing methods, as I was mentioning. So this is a free milling ore where the gold is actually easily accessible for leaching. So they do not actually do a lot of complicated beneficiation. They do use gravity separator. But other than that, once they produce the concentrate, they do direct leaching. They actually also leach the tails as well. So because they know they have some gold in the tail, they also leach the tail and the concentrate. And it's a relatively simple process. So obviously, in addition to the leaching that they do here, you will need to do with solid liquid separation where water is recovered and recycled back into the plant. And those big wells that you see, I don't know if you see in the picture there, are thickeners where water can be recycled back and reused. And in this part of Australia, water is actually very expensive and difficult to find. So you tend to find large thickeners like this to recycle the water back. And also you need to do proper tailing management as well. So whatever you put to the tails need to have a certain composition, a certain percent solid in them. So that is also managed through the use of thickeners and so on. Okay. So now that you have this picture, so what do we need to do before we go straight and try to beneficiate an ore or try to do mineral processing? The first thing you need to do is understand the ore. Okay, what do you mean by understand ore? You need to know what's valuable, what's waste. If it's a copper ore, how much copper do I have in the ore? Is it 1%? Is it 0.5%? Is it lower than that? Because if it's, for example, below the cutoff grade, there is no need to process it because you're not going to make any money, okay, because it is below the cutoff grade if it's too low. If it is high enough, usually in this part of the world is above 0.5% copper for copper, then you need to then come up with how is the copper associated in the ore. Is it copper in chalcopyrite? Is it copper in chalcocite? Is it copper in oxides? Because unless you know, just knowing that I have more than 0.5% copper doesn't mean anything. So you also need to know where the copper is located or what is hosting the copper. So if we know the copper is in sulfide, like chalcopyrite, then we can have a processing plant for it. If it's in oxide, then we can have a separate processing plant for it. So the processing plant is determined by the nature of the ore, because you're not going to have the processing plant first and then try to bring the ore. It doesn't work like that because your processing plant might be just a complete waste of money. So usually the processing plant is designed or constructed based on the nature of the ore we're trying to process. At least we need to have a rough idea of what we're dealing with. Okay, so that's the mode of occurrence and what is associated with it. So if it's chalcopyrite, what's the main gang? Do we have any trouble making gang minerals like clays, for example? So we need to know that. We need to also see what is the composition of the ore itself. So, okay, I have copper there. That's my main element. Sometimes you have good amount of gold with it, especially for copper. And many places actually produce byproduct, both copper and then the byproduct will be gold, some places even silver. So if that's the case, then you need to also know, are there any potential byproducts that I can use or I can extract? So we need to assess. So we say, okay, there is a bit of gold, but it's actually very tiny, so I'm not going to go bother with it. But sometimes once you upgrade the ore, you may have reasonable amount of gold and you might start to think about recovering that as well, which is very common to do if we have any byproduct gold anyway. And also, how fine do we need to grind it? Will depend on the grain size. Okay, so chalcopyrite, for example, I can take a microscopic image of a sample, do detailed analysis on it using, say, scanning electron microscope, and I can work out roughly the grain size. That tells me how fine or how coarse I need to go in order to actually separate and liberate it. So my grinding size, okay, during milling will be determined or dictated by the grain size I have in the ore. If it's coarse grained, no need to go fine grinding. If it's really fine grained and the minerals are complexly associated with one another, then you have no option but to do fine grinding. Okay, so that's what we mean by grain size, distribution, and shape, and also a number of other things, including the gang, boundary between gang and the target, and how the various minerals are linked with one another. And that image on the right simply tells you just an example of what you can do. Okay, so this is for a copper sulfide ore, I think, where the main mineral here is chalcocite, and you can take a number of samples, do maybe thousands of such analysis using an automated scanning electron microscope, and it tells you after milling whether you have liberated the particles or not. For example, the blue, in this case, is chalcocite. If the majority of them look like this one here, then you have liberated them, okay, after grinding. So there's no need to do further grinding. If after doing your grinding, you end up with the majority of the particles looking like this, then you have to do more grinding, because I'm not going to get any benefit from processing this, okay? Because the first stage should be liberation. And to determine what final grinding size I'm looking at, I need to do further grinding and be able to liberate. So these are the things that we need to consider in mineralogical assessment. So when I say liberation, maybe it all looks like this one. The yellow ones here or the orange ones are my target, okay, distributed all over the rock. I grind, ideally, that's what I want to produce. So these are all orange dots, which are free, valuable minerals. Now I can easily beneficiate this, okay, because typically the orange ones and the blue ones have different properties. So it's easy to do beneficiation on this one. But if I end up with something like this, not good, because still the target and the gang are associated with one another. If you wanted to have very good success in beneficiation, you need to actually consider grinding again. So regrind whatever you see here to be able to liberate them from one another, and of course talk about separation or liberation, beneficiation afterwards. Okay, so that's why assessment is very critical, and it needs to be done properly to maximize any profits that you might get from the plant. So once you do your assessment, you understand the ore, probably some of the key considerations are whatever sample you took for your mineralogical assessment, is it a representative of your sample, or is it representative of the pile? Because typically your stockpile looks like this one, okay? That is what is coming into the processing plant. If I just take a sample from here, it's not going to represent everything. If I take the sample from the top, it's not going to represent everything, because particles tend to segregate when you stockpile them. The coarse ones usually fall to the ground and they aggregate somewhere here, while the fine ones are somehow aggregated to the top. Usually what happens naturally is your target one or your valuable one goes to either the fines or the coarse, and usually goes to the fines. So whatever sampling you do should take into account that differences in properties of the material, should be able to capture whatever is coming to the stockpile. So instead of, say, sampling from here, the best way to do it is sampling from the belt. Okay, so maybe you can have a belt coming from the crusher to the stockpile, so I can take time samples from the belt and do assessment on that. Or once I stockpile, so people usually have feeders at the bottom of these stockpiles here, and usually the feeder will try to distribute the material. Okay, they may have maybe 3 or 4 different feeders at the bottom there, and they mix it up to get it to the crushing or grinding mill. So either you can take this belt or you can take this belt, but typically you probably would get a more reasonable homogeneity if you were to sample from here. So again, those are the things you need to think about. Unless you understand sampling, maybe someone may just take sample from here and say, this is my sample. If you do that, usually you end up with the wrong sample, and that's not representative anymore. But at least it needs to be done. Take time samples, could be every 2 hours. It could be maybe every 4 hours, whatever, but you need to take a reasonable sample by cutting from the belt and so on, so that you get a representative sample that you can work on for either mineralogical assessment or other assessments. Okay, so it could be for grade control, could be quality control, it could be to optimize your plant, or you may be just interested in what's coming to the plant. How many grams per ton of gold is coming to my plant? How many did I process in a day? How many did I process in a month? How many did I process in a year? So you need to also keep on those figures as well. So to be able to tell, for example, the mine manager to say, this million tons were processed, and of those, the gold was this much. To get those figures, you need to do constant sampling and obtain representative results. So this is very critical. So what I want you to know in sampling, at least from this course, is in mineral processing, there are specific ways of sampling ores. So I want you to understand those methods. And I want you to also understand key considerations. If you were to cut a belt, like this one, for example, or if you were to take a stockpile or whatever, it needs to be representative. And some of the requirements, for example, to make sure the sample is representative is, if it's, for example, a pipe, you need to cut the whole pipe. You need to block the whole pipe when you're sampling, not just the outside of the pump or the center of the pump, but the whole pipe needs to be cut, okay, when you're trying to do sampling. Because particles, when they move in a pipe, for example, they may segregate to the center or to the periphery of the pipe itself, which then brings bias. So in any case, whatever sampler you use needs to cut the entire stream. And typically it's better to give it a constant time for it to sample. Okay, instead of just sampling in the morning and in the evening, and you have no idea what goes during the day, it's better to take regular samples, maybe 4-hour samples or 10-hour samples, so that you keep an eye on how the whole process runs. Okay, so those are the main requirements. And if it's a belt, of course, it needs to cut the whole belt from the top to the bottom, because we know particles can segregate, fine particles can go to the bottom of the belt. If you're just scraping the top, then you miss the fine particles. That's why we say you have to cut the entire stream as well. So at least I want you to understand these considerations when you're thinking about sampling of rocks, okay, especially in mineral processing operations. So usually it's either a belt, okay, or free-falling stream, or it is in a pipe. Typically, that's how we transport material in a mineral processing plant. So in each of those cases, cutting the entire stream will be a requirement, and maybe making regular cuts is a requirement. Okay. Okay, so what is another consideration in this unit? Yes, eventually we want to do particle separation or valuable from waste. But before we even get there, we need to do, as I said, proper level of grinding. Unless you achieve proper grinding and you have liberated sufficient amount of particles, your separation is going to fail anyway. Your beneficiation is not going to be successful. So always it's better to achieve the required particle size based on the liberation studies you have done. And I think I asked you this question in the past as well. So, but when we grind particles, obviously we're going to produce different particle sizes in a mill, or we're going to produce different shapes. And therefore, the way you quantify that needs some kind of agreement, some kind of understanding. So that's why we use particle size distribution analysis to be able to have a standard method of quantifying particle size distribution. Okay, so again, as I said, could just be controlling liberation, or you know the final product size you want after the milling process, but you want to keep an eye on your mill. Is your mill operating at that required particle size? And usually what people do, they put at the discharge end of the mill, they put a sampler, take samples, do particle size analysis on that. And you can even use auto samplers, which automatically sample the discharge from the ball mill, for example, and they give you the particle size reading already automatically. And this is inline samplers and inline particle size distribution analysis. So in the bigger plant, that is possible to do. So then I know what is my P80, for example. That's the typical figure that we want. Is it varying day by day? Is it always constant? Is there anything that I'm seeing? Because when you mine, the ore composition varies. Okay, maybe sometimes you tend to hit a soft spot in the mine, and sometimes you hit a hard spot on the mine because you're not nicely blending it. If you're just bringing the material as soon as you mine it, there is a significant variation to what comes to the mill. Okay, so when you do milling, your particle size distribution varies greatly, your P80 varies greatly, and therefore you need to keep an eye on what's going on. And the best way to do that is, of course, to do particle size distribution. And also when we feed the next step. So as I said, you mill, and then maybe you send it to gravity separation. you mill, and then you send it to flotation. But these processes are size sensitive. For example, if you feed very fine particles to flotation, it doesn't perform well. Okay, so typically if you have, say, below 20 micron particles, those are very fine to actually have efficient. You can still do flotation, but they're challenging to float them. Okay. And the same is true for gravity separators. If you go below, say, 50 micron or somewhere around there, your gravity separators start to struggle. There are some that can handle, like Nelson concentrator and so on, they can handle very fine particles, but most gravity separators struggle for fine particle portion. So again, you need to keep an eye on what goes into the next step by doing proper particle size distribution. So it's very important step in any mineral processing operation. That's why we need to know about it. That's why we have to understand a proper way of doing it. Probably in many places, sieving is by far the most common. I think in many places I went, in the local mineral processing sites, most of them use sieving. Okay, and I went to, I don't know how many, maybe 50, 60 places, and it's cheap, and the particle sizes that you're dealing with are what we normally expect in mineral processing plant. Okay, so we do crushing, grinding, after, say, ball milling. Most of the particles are somewhere between, say, 10, 20 to about 200, 300 micron. So it works well in that range. Okay, theoretically, you can have large sieves with 100 millimeter, 200 millimeter or more. Okay, but typically in mineral processing after grinding, you tend to get particles between 20 to about 250, somewhere around there. Okay, if it's cold, maybe you can go a bit higher. Okay, if you're using dense media or gravity separators, maybe you can go up to 500 micron and above that. But in many places, whatever size you're dealing with, sieves can handle that really well. So that's why they're common. They're cheap to run. You don't need any fancy equipment there. So they're very practical. Even in many labs, also you can find sieves. So they're very effective. But if you can afford them, you can also complement the results from the sieves using, say, other methods like illustration or laser sizer and so on. Okay, but typically sieving can be one of the better ways of controlling or keeping an eye on particle size distribution. And by now you should be very familiar with how sieves work. And probably one of the standard, I guess, figure that people use after sieving is the P80, or the 80% passing size. So after typically you doing your sieving for particle size distribution, you might be asked to determine the P80 size or the 80% passing size. Okay, maybe that figure is then used as a standard throughout the plant to control either the grinding efficiency or to control what goes to the next stage processing. In some places, they actually have their own standard chart, so they can use the Gordon-Schumann plot, or they can use Rosen-Ramler plots and so on. Those are more standard if you want to have a better control on particle size distribution. You can use those plots as well. So I've shown you how to do those. At least if you have to learn one, I would urge you guys learn how to at least analyze data from a sieve analysis, because that's very common. You can easily do that in many places, and gives you reasonable information for particle size distribution anyway. So if you determine the P80, then you probably can get away with many places and get a reasonable particle size distribution. So again, this can be just, it's an example. This table shows an example of what information you can get using different sieves, masses in each sieve. You can work out the percent and then the cumulative passing, and the return can be worked out. So at least I expect you to extrapolate or calculate this table, complete this table based on, say, these two rows that are given to you. Okay, sorry, these two columns. You can do these two columns in the lab. then you need to learn how to do and complete these three columns. Okay, so again, typically once you do that, we have what we call the P80 or 80% size, passing size, which can be a guide. So you say, yes, I've taken example, done particle size distribution using sieving method, and your P80 is this much in micron. Okay, so you should be able to learn how to do this. At least I expect you to. But it's not, it's not the best way of reporting particle size distribution, because all it says is the 80% passing size is this. It doesn't tell you what is going on below that 80% passing size, because different particle size distributions can have the same P80. Okay, so maybe this one is shown in this distribution here, but it's possible that maybe you can have another distribution that follows something like this, still passing through the P80. I can have other particle size distributions that may look like this. So again, it doesn't tell you what happens below or above that particular size. It's a very crude way of reporting particle size distribution, but it is probably one of the most common figure that you find in many places. So if you ask someone, so this is the mill I'm using, this is this, and you say, okay, so how do you check your grinding performance? Usually they say they have a P80 of this, and that's how they control what fraction of particles they're producing after grinding. Okay. As I say, it doesn't tell you everything, but at least that's what we have as a way of telling particle size distribution. Okay, so again, once you learn how to do this, obviously, that, as I said, this is, at least I expect you to learn how to do this. Another very common operation in processing plant is metallurgical accounting. So some of our graduates, I go there and ask them, what is your everyday activity? They say maybe early in the morning, every time they go to work, they have to do metallurgical accounting. They complete a spreadsheet or they complete a table to do with accounting. So what is metallurgical accounting? It's all about how much material did we process in a day, in an hour, and in a year, and so on. Because the managers always want to process lots of material. Maybe their target, I don't know how you call it back home, but when you have a processing plant, usually they say, I need to process 2 million tons per year. So that's what the manager wants. That's your target, KPI, or whatever it's called. So all the manager wants is whether you have processed 2 million tons in a year. Okay. But every day you need to add up the individual processing tonnages per hour, per day, per week, and so on to get to that year. And you need to do proper accounting to be able to reflect that figure. Okay. Not only that, it's probably not good enough to just say we process 2 million tons per year. You probably have to also know how much gold went through the plant in that year, if it's a gold plant, or how much copper went through the plant. How do we know that? Because we know the head grade or the feed grade. We know the total amount of material processed. We can then calculate the percent or the amount of copper that went through the plant in a year. So the other thing you can also do is, yes, we processed 2 million of that. This amount was copper. So you say, then we recovered 90% of it. Maybe you recovered 80% of it, and so on. Again, how do you know how much you recovered? You also know how much went to the concentrate during your mineral processing, how much copper went to the tails and lost during your processing. How do we do that? We take samples from the concentrate and the tails. We analyze that. We take the average over a year. We can also work out how much was lost to the tails, how much was recovered in the concentrate. Then the figure will show you the grade or the recovery and so on. So you could say 90% recovery was our plant performance. Maybe you targeted for that, maybe target below or above that, then that's how you assess the performance. If it's below performance, Usually it's to do with how you operate the plant, of course, but also what were the variations in mineralogy during the year, okay, and things like that. But in any case, methodological accounting is very critical. We do that almost on daily basis, and it involves something going to the feed, going to the plant, and being recovered into the concentrate and the tails. And the way we do that is we know the masses, okay? Maybe in this case, you take samples from the belt, you know the tonnage on the belt, you can work out feed mass, feed tonnage, or capacity, whatever you call it, and you know how much concentrate was produced, how much goes to the tail. So the masses are known, so you can do mass balance. And we can do specific balance for the copper, as I said, okay? So the small f here is copper in the feed, the small c is copper in the concentrate, and the small t is copper in the tails. So we can also do the balance for copper. If it's gold ore, balance for gold. Any other thing, the same. We can even do balance for water, okay? This much water was used in a plant in a year, okay? So you can also talk about that. Maybe you can divide the water into whatever came to the plant and whatever was recycled, and the combination of that will give you the total water balance. So at the very least, in a processing plant, the metallurgical accounting should involve the total mass or tonnage, how much amount of material was processed in a year, in a month, and so on, and how much valuable material was processed. So that will be, in this case, the commodity, copper, gold, or whatever, water balance, and so on. So you can do a number of these and obtain whether you are meeting figures, whether you are meeting the target or not. And one of the things that you will do is recovery, of course, as I say. So recovery mainly deals with material recovered in the concentrate for the valuable. So in this case, material could be copper, or it could be what is hosting the copper. If it's chalcopyrite is a copper mineral, so it could be chalcopyrite recovery, could be copper recovery, and so on. If it's gold, again, it could be gold recovery, or it could be what is hosting the gold. Could be pyrite, any other mineral that's hosting the gold. So recovery is whatever is in the concentrate times the mass of the concentrate divided by the feed times whatever valuable you have in the feed. So those are fractions, okay? So again, I think calculating recovery is probably one of the simplest things you can do, but to get to that, you need to have done a proper accounting of what's going on. And eventually, maybe you have what we call grade recovery curve. So when we say grade and recovery, so if I say go and do processing of the ore, as I said, whatever you do here could be flotation, could be gravity, could be magnetic separation, whatever it is. Usually you produce a concentrate and tails. So the recovery is, as I said, whatever went to the concentrate divided by whatever was in the feed. So in this case, you can either push the quality of the concentrate. This is, for example, I want a large fraction of copper in my concentrate. That's the grade of copper. If you try to push the grade, usually your recovery drops because we're trying to get a high quality copper. We're trying to reject as much of the waste. Usually when we try to reject much of the waste, what happens is some of the copper will be lost with the waste. So your recovery drops. So grade and recovery are competing against one another. So if you wanted to get high recovery, usually your grade is low, okay? Or if you wanted to have a very high grade material, your recovery is low. So at the end of the day, a plant operates at an optimum. So you need to do trade-off between grade and recovery. You say, okay, let's work at 80% recovery, okay? And you can say the minimum grade would be this much, okay? So you can always have that as a target. If the grade decreases, what you can do is you can now look at, okay, my grade is decreased a little bit. So what can I optimize in the process to bring it up? When you do that, you might reduce the recovery a little bit, which is fine. Okay. So we'll talk about maybe flotation in particular in the second semester or whatever semester you are in. But for example, typically in flotation, we have a number of stages. We do a roughing stage, we do a scavenging stage, and we do a cleaning stage. All of these have different priorities. For example, in roughing stage, all we do is just try to maximize recovery. Okay. And once we do that, in the cleaning stage, we try to maximize the grade. So in this case, we might lose some material, but the idea is to produce a high grade or a high percentage of valuable material in the concentrate. So these are competing, but this can be managed based on the different stages of processing you're doing, okay? But at least what I want you to know here is there's always that competing interest between grade and recovery, and your metallurgical accounting or mass balancing may be designed based on those competing requirements as well, okay, to get to the required or the target plan. So again, you're not going to do that just for the crusher. You will probably have to do it for everything you do. So your crusher may require a separate metallurgical accounting for water, for material, for the valuable. Your mill, your grinding mills may require that. You may even have a thickener where you probably are interested in mainly keeping an eye on the water balance, how much water is being recovered from my thickener, okay? You can do that for leaching, where I have put this much gold into my leaching tank, how much of it is dissolved, how much of it is not. And you can do metallurgical accounting for a large portion of the circuit or the flow sheet that you have. So this is actually the same plant. So this is the same plant, but as you can see here, it looks simple here, okay? But when you look at the actual flow sheet, it's actually a lot more complicated. And those lines here will show you different material splitting into different regions and then combining to form a new stream. So when streams combine and split, obviously the material also combines and split, water combines and splits, and the valuables, the copper, the gold, also split and combine. So you need to account for all those to have an accurate reading of what's going on. But at least, again, what I want you to understand is in metallurgical accounting, we need to do water balance, mass balance, and valuable commodity balance at the very least, okay? So these are something you do on daily basis. And again, I think it's simple calculations at the end of the day, but it's more to do with understanding the importance of metallurgical accounting, okay? So we have done a couple of tutorials on this one. Probably you have done similar tutorials for other courses as well, because as I said, you will do this for material handling, you will do this for hydrometallurgy, you will do those for crushing and grinding, for all the operations. So I wouldn't be surprised if you see metallurgical accounting done for a number of courses. But at the end of the day, I don't think it's redundancy. I think it is more to do with understanding different processes and learning how to do proper accounting. So that should be, I think, a good way to proceed. Okay, any questions so far? I don't know, I think I'm talking a bit too much on all the points. I don't want to bore you guys, but hopefully it is going okay. But any questions? Okay, so we talked about comminution, which we said includes crushing and grinding. In mineral processing, the main reason that we do comminution is to liberate particles or to produce free particles. So this can be the valuable, it can be the gangue. If you liberate the gangue, it's good. If you liberate the valuable, it's also good. So liberation is typically done for both the valuable and the gangue. And the main purpose of comminution is liberating particles. Yes, you can use it to increase, for example, surface area of particles to prepare them for leaching, flotation, and so on. But at least in this course, the main purpose of comminution is producing free particles. I talked about different way of doing it, depending on the energy or depending on the mechanism of breakage you apply, you can produce different size particles, you can produce different distribution of particles. So probably there's not much into this one, but I encourage you to go through and understand each of these concepts at least. So when you say abrasion, for example, in ball mills, abrasion is applied where particles rub against one another, against the media balls that we add into the mill. Because of that, we tend to produce large fraction of small particles. While in crushing and grinding, in crushing, primary crushing in particular, the main purpose is not liberation, but the main purpose is handling the rocks. So instead of dealing with 1 meter rock, the main purpose of a crusher is to reduce that size, okay? And maybe you go from 1 large rock to maybe 3 smaller rocks, okay? So that's typically what we use in crushers. So that's why we use a compression force rather than rubbing or abrasion force, okay? Impact crushers can also be used as primary crushers, but they're probably less common in mineral processing. They're probably more common in making roads, making material for building, and so on, rather than being applied in mineral processing. So typically, if you ask me, compression tends to be a more common crushing mechanism, while abrasion tends to be a more common mechanism in ball mills and road mills and so on. So how do you design a combination circuit and what are the key considerations? So because combination or grinding in particular is energy intensive, we're always concerned with energy. And usually the amount of energy you spend depends on the nature of the material, okay? But it depends on the nature of the crushers and mills that you are also employing. So again, when you design your flow sheet for combination, the key considerations will be how much power am I going to spend, okay? And therefore, based on that, what is the nature of the ore? And so what am I going to select? Which mills are more appropriate for my material? Okay, so as I said, soft rocks do not need complicated crushing and grinding. Maybe one stage will be enough. So the hardness of the rock will be one of the key factors. That's why we say required power depends on the nature of the rock. But the amount of power you spend also depends on the nature of the crusher used. Okay, because they have higher power draw. For example, a SAG mill has a higher power draw compared to a ball mill. So if there's no need to use a SAG mill, then avoid using it. Okay, but if you have competent rock, very hard rock to deal with, then you probably need a SAG mill. Okay, so then the nature of the rock will depend. The nature of the rock will dictate what kind of crusher or grinding mill you're going to buy. And that type of grinding mill will also depend on, of course, its power requirement and everything else that comes with it. And also the initial and final product sizes. Why is this important? Again, initial probably is easy to control, but the final product size depends on what happens next to the particles, as well as whether you have sufficiently liberated the particles. So if we say my next stage is flotation, and I already know 100 microns is sufficient enough for liberation, perfect. But sometimes what we have is a situation where you have to mill it to 20 micron, and the subsequent process then may struggle. For example, if it's 20 micron, 10 micron particles for liberation, you try to follow that up with flotation, you might be okay, but you're going to struggle with upgrading, okay? So these are some of the key considerations we need to take when designing a circuit. So in this case, it's not good enough to say you first come up with all the equipment, you know the best operating parameters for the equipment. That's not going to make you successful. The first stage would be, what am I going to process? What is the nature of the material? What is the energy requirement? What's the crushing and grinding requirement? Once you know that, then you can come up with the most ideal flow sheet for it. So that's why usually I say mineral processing usually tends to be very site specific. So depending on where you are from place to place, and you find different processing methods. And in many places I went to, I never found an exact copy of one flow sheet in another place. So usually there's some change from one place to another. And this is, I'm not talking about maybe places that are far from one another, even for gold processing plant, which are maybe like 200, 300, 20, 30 kilometers apart from one another. They still produce gold, but they still have different processing routes. And the material dictates the equipment selection. So they use different equipment. You can have a general guide. You can have, so for free milling gold, this is what I'm going to do. For refractory gold, this is what I'm going to do. You can have a general guide, but usually the details of specific things you do, the specific flow sheet that you have, will depend on specific requirement of your ore and its mineralogy. Okay, now by now you guys should be very familiar with this. So what I want you to know here, I want you to know grindability doesn't mean hardness. Okay, it just means an ease of grinding the ore. Okay, so grindability simply tells you how easy or how difficult it is to grind the ore, and usually that is between two ranges, between the feed size and the final product size. Okay, for the same material, for the same ore, if my product and feed sizes vary significantly, I will have different grindability, because smaller particles are difficult to grind, while coarser particles are easy to grind. That's why we say even for the same material, grindability may vary depending on the final product size. So that's why we put, or in this case, we include the final and initial product size to get an idea of how much energy or how much power we're going to consume during grinding. So at least I want you to know the Bond's work index and how it can be determined for any given sample. Okay, if I give you a sample and I say, please determine its Bond work index, I would expect you to at least know how that can be done. And at the end of the day, I want you to give me a figure and say, this is the Bond work index, and depending on the experiment I've done, this is what it shows. Is it hard rock? Is it soft rock? And so on. So at least those are the things that I expect you to know. But there are a number of other methods, like the drop weight test and so on, where you can also use to determine grindability of the ore as well. Okay, in terms of power consumption, crushing doesn't take a lot of power, but grinding consumes more. So in fact, more than 90% in a given operation is actually consumed, or the energy is consumed on the grinding part. Only about 10% or less is consumed on crushing part. As I said, because fine particles, which we do grinding on, are more difficult to break and produce finer particles compared to coarse particles. So that's why crushing doesn't take more energy, while grinding takes. So in this case, if you want to save energy, avoid over grinding. Okay, in this case, try to get rid of the product from the mill as soon as possible. That's one way of avoiding over grinding. And also, whatever you recycle back into the mill needs to be of controlled size. Okay, and some places are actually trying to minimize the grinding by trying to do both crushing and grinding at the same time. So instead of, for example, using a compression force, they're trying to use something that incorporates both the crushing and grinding in one equipment. And you have something that looks like a impact crusher and a gyratory or jaw crusher, and in the same one step, you can do both the crushing and grinding. And if you do that, obviously you're going to maximize breakage and improve energy consumption requirements in a processing plant. Again, this is only a guide. Okay, so I've shown you this before. May not need 3 crushing stages, may not need 2 grinding stages. You may need all of them. Depends on the nature of the ore. But typically in crushing, primary crushing deals with reducing particles from about 1.5 meters, somewhere around there, to about 100 millimeters. That's the expectation of a crusher. If you're using secondary, tertiary crushers, maybe the target will be somewhere, usually around 50 millimeters. That is your product from a crusher. This can now go into a primary grinding mill for grinding and produce particles as required. So this is, again, rough guide, can be varied depending on what's going on. So you probably know now we use jaw crushers, gyratory impact crushers as primary crushers, but I want you to learn about how each of them work. Okay, so what's the mechanism by which a jaw crusher operates? What's the mechanism by which a gyratory crusher operates? So I want you to learn those and where are they going to be applicable. Okay, and also especially in terms of flow sheet development. If, for example, I say I actually require, I have a competent rock hardness of maybe about 15 kilowatt hour per ton. My capacity is around 400 tons per hour. When I mention those things, I'm hoping, obviously, maybe you're thinking more like a jaw crusher rather than a gyratory or impact crusher. Because when we think about what we need to put in a processing flow sheet for comminution, capacity usually is considered. Usually the hardness of the rock is considered. And if your capacity is below 500 ton per hour, if the rock is not really hard, competent rock, but not really hard, then you're probably looking at jaw crusher. But if I say, oh, I actually look at an operation that is about 2,000 tons per hour. Okay, 2,000 tons per hour, reasonably competent rock, maybe hardness or work index of around 13. Maybe in that case, you might look at gyratory crusher because of the capacity that you're looking at. Instead of buying 3-4 jaw crushers, it's a lot more desirable to have one big gyratory crusher that can handle this. So again, these are some of the things you can consider. And also, are you going to mine different places? Is your plant mobile? If it's going from one place to another and you're doing this over the year, to move things around, a jaw crusher is a lot more easier. A gyratory is probably something that's fixed, as you can see here, in the ground, and you're probably better off buying a jaw crusher. So consider some of those things. Okay, and is feeding a problem? If you have issues with trucks, then self-feeding properties are more suited for gyratory compared to jaw crusher and so on. So at least I don't want you to know everything about it, but at least I want you to have an idea of how they work, the working principle of gyratory, jaw crusher, and so on, and what are the rough considerations in terms of, for example, capacity, feeding properties, and things like that. Okay, so that you have a good understanding of what requirements have for each of them. Okay, again, for the grinding stage, what is more important here is in grinding, we can have grinding as the final stage of the comminution process. So again, here, when we talk about grinding, we're typically looking at, we have now liberated the majority of the particles. That's the stage where we are at. If your grinding doesn't give you liberated particles, then it's not a successful grinding stage. So as I said, always, grinding flow sheet is designed around the idea of being able to produce liberated particles. And that will be obviously dictated by how fine or how coarse the particles are. So your mill, your grinding stage should be able to achieve those particle sizes. Okay, so as I said, grinding, especially the ball mill stage, works well until about 75, 80 microns. If your product requirement is, say, about 20 micron, then maybe ball mill is not going to be enough. Okay, so you need to be thinking about other methods like ultra fine grinding. I will mention that a bit later as well. In any case, in grinding, we usually use a media. So what's the media? It could be rods, it could be balls. If it's a SAG mill, could be just rocks, hard rocks, or maybe a small fraction of very large balls that we can put in a SAG mill. But in any case, the media can be a ball, it's a ball mill, a rod, it's a rod mill, or rocks, that will give you a SAG mill. And the idea here is to produce something around here, so between 300 micron and about 70, 80 micron. If you push it, you can go down, but we know it's not going to be effective. At 10 microns, I will be already asking you questions. So if you say, actually, my plant is using ball mill as the final stage of grinding, and my target particle is 10 micron, I say, oh, okay, you have a problem here. You can achieve it, but you are wasting a lot of energy, you're recycling a lot of material, so it's not an effective combination circuit. So I'll probably say, why don't you use maybe a ball mill followed by an ultra-fine grinding circuit? Okay, so usually, although we say grinding mills work well below 100 microns, the limitation usually is below about 70 or 80 microns. They don't perform well. And in fact, studies have shown that of all the power we use during combination or during crushing and grinding, only 1 or 2% is actually used for breakage. All the other energy is lost as heat, and that is a problem. And that is usually to do with not finding the best final product size for the grinding mill. Okay, so again, different types. Could be tumbling, stirred. These are more coarse grinding. These are more fine grinding. And during grinding, what I want you to know is also the so-called critical speed of a mill, especially if it's a tumbling mill. As we said, if you rotate particles too much, if you rotate the mill too fast, we start to have a problem with particles and everything in the mill sticking to the wall and nothing much happens. So we need to operate at a fraction of the critical speed. So critical speed can be calculated based on mill diameter and ball or media diameter. And usually it's better to work as a percentage of that, so between 50 and 90% of the critical speed. Okay, so why do we have such a large range? Usually rod mills work at a lower end of the critical speed. If you're using SAG mill, we work at the higher end of the critical speed. Okay, ball mill, usually somewhere in between. And that's again to do with avoiding centrifugal force, taking everything and sticking to the wall where now nothing happens even though you rotate it. So always mills are operated at a certain amount of the critical speed. So if you look at SAG mill, okay, where in SAG mill now we have maybe 10 to 12% of media. In media, for example, I'm talking about 125 mils ball, steel media. The remaining will be hard rocks plus soft rocks. The rotation for the mill that we're looking at is somewhere around 11 revolutions per minute. And this could be, say, around 75 or so of the critical speed. But that depends on obviously the mill diameter and so on. So you need to calculate whatever critical speed you have for a given mill based on the dimensions, which is not difficult to do. And for example, if you're operating a SAG mill, we also use water, and typically densities are about 70 to 85% solids. So one of the main difference between a SAG mill and a ball mill, because they're both tumbling mills, they use ball as a media. One of the main differences is SAG mills are very large in diameter compared to their lengths. So in this case, for example, this is the length and 8 meters is the diameter. But SAG mills can be up to 12 meters in diameter. So we make them really large in diameter, but shorter. Why do we do that? Because we want to obtain sufficient impact, sufficient power in the mill. We want particles to go from a higher height and fall down. So the impact inside the SAG mill is very high. And usually you start with particles that are 50 millimeter and you just grind them easily to about 5 millimeters in one go. Okay, so that's why The power is very high and very effective as well, especially for hard rocks. Then usually we put a screen in the discharge end of a SAG mill. And with that, the SAG mill produces, for example, in this case, I think this example shows the aperture of the screen is about 8 millimeters. So coarse particles will go to a secondary crusher and will be crushed and brought back into the SAG mill. Fine particles can be sent to the ball mill, can be sent to a storage, and so on. Okay, but at least here, I want you to understand that SAG mills have a larger power draw, which then makes them effective for primary grinding stage. And as said, usually the oversize from a SAG mill is crushed using a recycled crusher. Usually we use a smaller cone crusher for this purpose. For example, you could have produced 8 millimeter and more particles as oversize from SAG mill. Then that can be crushed again with a recycled crusher and then put back into the SAG mill again. And typically, if you're using a recycled crusher, the product that you expect is somewhere around 15 to 20 millimeters that can be, again, crushed and processed further in the SAG mill. So typically, we have what we call the ABC circuit. I will show you a figure in another slide later on, which involves a SAG mill, a ball mill, for example, and the cyclone, but in between those, they will have a crusher. Rod mill, probably what I want to emphasize with rod mill is actually becoming a little bit outdated. So in many places, you don't find rod mills. They're being replaced by a SAG mill. So it's becoming older technology. But if you do, then you have rods instead of the ball. And again, it's horizontal tumbling mill. And we usually rotate the mill at about 50 to 75% of the critical speed. And the majority of it is occupied by the rods, so about 45, 50%. The same with the others, so the same with the ball mill and with SAG mill as well. A large proportion of it, not SAG mill, a ball mill. A ball mill may have about 50, 45% of the volume occupied by balls, and a rod mill about 45% of it occupied by the rod itself. Probably one of the interesting thing about rod mills is you tend to produce a uniform particle size as a product. Okay, that's to do with selective grinding happening in a rod mill. This is the feed end, this is the discharge end. Particles that are coarse usually are at the feed end. And because this open area here allows particles to freely move, usually you don't do over grinding in a rod mill. So usually it's desirable if you want to produce uniform size particles, rod mill is a lot more effective. And maybe if there's a particular requirement to produce uniform particle sizes or narrow range particle sizes, maybe it's a way to go with a rod mill. Okay, so with ball mill, again, balls instead of rods are used. An example of mill rotation, somewhere around 14 revolutions per minute, operated around 70-75% of the critical speed. And density that we're targeting is around 70 to 80% as well. And usually the balls that we use are around 60, 65 millimeters in size. Some places use smaller balls, maybe 50 millimeter and so on, depending on how fine you want to go with grinding. But typically it's about 60 millimeter grinding media in diameter. And this, for maximum operation, you probably would need to fill half of the mill with the balls themselves to obtain a reasonable grinding happening. Stirred mills are used if you want to do fine grinding. So as I said earlier, if my target is producing 20 microns or 10 micron particles, probably ball mill alone is not a good idea. Although you can achieve it, you're going to spend a lot of energy trying to achieve it. So if my target is, say, 10, 20 micron as product size, typically people use attrition mills. So attrition mills, you have a feed coming here with water, you have a screw agitator, and the mill itself is actually vertical rather than horizontal. So what happens is we use very fine media. Instead of, say, 60 millimeter ball, we use 5 millimeter ball. So already we're using small balls in a stirred mill. Could be made from ceramics, could be made from steel, but they are very small in size, which means they have larger surface area compared to large balls, okay? And we also have a screw agitator, which means you're going to produce a lot of attrition inside the mill itself, because this screw agitator moves the particles, the small ball media, and so on. And that's going to give you very high contact between the ball and the particles. And you tend to produce fine particles, or we call them actually ultra fine particles. So if particles are below 20 micron, usually we call them ultra fine particles. Okay, it's just a terminology. And so in this case, you do that, you produce fine particles, you have the media and the particles where you have a separator, which recycled the ball or the media back into the mill, while the product is recovered as a fine material. So a lot more effective compared to ball mill if you were to do ultra fine grinding. So this is a vertimill, or a vertically erected mill. But in Australia, people have also designed what we call Isa mill in place called Mount Isa. Instead of vertical, this is horizontal. And instead of screw agitator, you actually have disc. So these discs here that are shown in red here are rotated inside the mill. So you feed the particles, you add very tiny ceramic balls, and basically you rotate everything at very high speed, including these discs here, and you're going to produce a very high contact between the media and the particles, and you produce very fine particles. So again, they use it because they need to produce about 10 micron, 12 micron particles as product. They can even produce 7 micron as product, and these places. And it was designed based on necessity, basically because their liberation was very fine, because their copper, lead, zinc ore was very fine in liberation. They had to come up with a new technology because ball mill wasn't effective enough at that particle size. Okay, but again, these are some of the recent technologies or advancement in comminution. So again, there's a bit of a controversy. Some people don't want to say this is a comminution stage, but in these places, obviously, it is a comminution stage. But in many places, you can also find this kind of mills as a regrinding mill. So you do your ball mill, you separate the fine from the coarse. The coarse ones can be reground and put back in the mill. Okay, so for those purposes, you can actually use them for regrinding purposes as well. But you can also incorporate them in your grinding circuit as well. High pressure grinding rolls are again more recent technologies. I talked about roll crushers, I think, in one of the crushing lectures. So high pressure rolls are actually different from conventional rolls because people make them very large. So these rolls here are very large compared to the length. So typically the ratio of length to diameter is somewhere between 0.1 and 0.5. And because we make them very large, they actually have a very high nipping energy. So this could be compression of around 200 newtons per millimeter square. So this is actually a very high compression force applied to the rocks. So instead of just compressing them, we actually have a very high impact force, excessive compression, if you like, which then smashes the rocks and produces loss of fracture inside the rock. And you essentially tend to produce a cake, which then, if you send this to a a grinding circuit, it grinds very quickly. So this is one of a recent technology where people are trying to save energy by producing loss of crack inside the rock. And by that, they're facilitating their grinding operation. Where do you use this? This is typically used when you have very hard competent rock, which is hard to grind. You can actually use high pressure grinding rolls to be able to attain a reasonable grinding efficiency. Okay, so I have talked about this one. I don't think there's a need to repeat this, but I expect you to learn. So I brought this slide here for you to go through the tutorial and also your notes and understand what is the effect of mill speed, what's the effect of grinding media, and so on, volume of grinding media and so on grinding rate. Okay, so you can read through the tutorial notes, or you can read through any other resources, but I expect you to understand the effects of each of these on grinding rate. Okay, so in terms of what kind of circuits we use for crushing and grinding or in combination, depends on what you have available, obviously, whether you can afford it or not, but critically also on mineral characteristics. So what kind of ore do I have? What's the liberation required? What's the hardness of the rock? And so on. So mineralogical characteristics are very critical in designing circuits for comminution. And also, what do we do with it next? What's the downstream processing like? Can they handle fine particles? Can they handle coarse particles? And so on. So those are the key considerations in terms of your circuit design. So I think in one of the assignments, in the first assignment that I gave you, so it is asking you to study a particular comminution circuit, and it's asking you to comment on whether that was appropriate or not for the particular ore that's being processed in that place, and so on. So at least I would expect you to consider some of these factors. So for example, because this place is processing this type of ore, and this is the hardness of the ore, and so on, they have a typical crusher, typical mill, and so on, and they have to do several stages of crushing and grinding because of the mineralogical characteristics. So I somehow expect you to relate the circuit that you are studying to the nature of the ore that they're processing. Okay. And also, if you can find information once combination was done, sometimes if you have the whole flow sheet, you can see what's going on next. Okay, so they will have a flow sheet showing crushing, grinding, followed by maybe gravity separation, followed by flotation, and so on. Although you don't need to know a lot about flotation and gravity separation and so on, at least you can have an idea of what's going on, what the next stage of processing is after combination. So you can mention some of this in your responses when you complete the assignment. Again, so in this course, what are we trying to do? We're trying to achieve, or at least have an understanding of what is involved in a typical combination circuit. So we know primary crushing, typically we'll have another stage of grinding, and screens are typically used after either crushing or a primary grinding operation. And if it's a SAG mill, typically a SAG mill is operated with a recycle crusher. Okay, so I talked about why do we use recycle crushers and so on in one of the lectures. So have a look at those in grinding section. And of course, once you have undersize from a screen, that can be sent to a classifier, or that can be fed straight to a ball mill, and the ball mill is operated in closed circuit with a classifier. So at least you have crushing and grinding happening, but with them, you also have screening and classification. So you can't just talk about crushing and grinding without talking about screening and classification, because those are the ones who control the product size from a crusher and the product size from a ball mill or a grinding operation. Okay, so usually we operate them in closed circuit because we want to control the product size. Okay, so that's why we talked about screening in this course. Typically, in a simple sense, if you have a banana screen or a vibrating screen or whatever, the idea would be you have a sieve with known aperture sizes, you feed the material, fines pass through, coarse just flows over, and you have two streams, coarse and fine. But obviously some screens can have multiple decks where you can produce coarse, intermediate, and fine particles, okay, depending on the number of decks you have. And of course, depending on what kind of screen you have, it can be operated in a number of ways, okay? For example, here you have, if it's a banana screen, typically we tend to make it steep at the feed end, then the slope decreases gradually. Some like Grizzlies are not really steep. Even vibration screens are not really steep. And also the aperture sizes we use will be determined by what kind of or what size of particles we're processing. If it's controlling a feed to a crusher, usually we want the screen to be very hard. So we use Grizzlies for that purpose, because we know we're feeding them 1 meter rock or 1.5 meter rock, and they need to be strong enough to actually stand the pressure of very large rocks. So Grizzlies are typically used for those purposes. But for places where you have sticky rock or sticky particles, you might consider doing wet screening, okay, and things like that, or you might apply vibration and so on. So obviously where you use what screen will depend on specific application that you have in mind as well. But when we talk about screening, typically is particles above 0.5 millimeter. If you want to screen something that's finer, then you probably are not going to be effective. So you probably have to use a classifier. Okay, so that's the main difference. And I also went through some of this in the class. So you probably have to go back and try to understand the effect of each of these factors on screening performance. And for classification, you can have a number of classifiers, but by far the most common one is hydrocyclone in many places in processing plants. And again, what I want you to know here is at least understand the basic working principle of hydrocyclone. So hydrocyclone, as you can see, is conical in shape, cylinder with conical shape. Feed comes from the top and it goes in a tangential motion, typically swirling inside the cyclone. And as we said, if particles are coarse, they will attain a centrifugal force. They will be drawn to the wall of the cyclone. If particles are dense, again, they will attain a net centrifugal force. They will be drawn to the wall of the cyclone. Fine particles will be dragged to the center because of drag force. That's how we attain separation between coarse and fine. Okay, so coarse particles eventually exit as underflow. Fine particles eventually exit as overflow. Again, because they are very simple in construction, they're compact, they don't take a lot of space, they don't even require a lot of capital. They're very popular. And if you operate them properly, they're actually very effective as well. So probably one of the main issue with them is if you don't control the performance of a cyclone, you may have very poor outcome. So we need to keep an eye on how effective the cyclone is. And for that, we need to take information from feed particle size distribution and particle size distribution of the overflow and the underflow. We assess that. And we see from a typical partition curve whether your cyclone is actually performing at a reasonable rate or not. Okay, so efficiency can be worked out by constructing partition curve. And the partition curve is basically all about minimizing A and B here. A is because of the possibility of fine particles going to the underflow. Usually this is fine particles being carried with water to the underflow. Or you can have particles directly going to the overflow without being classified. Again, this can be represented by B here. And if the inside of the cyclone, the working condition of the cyclone, the pressure drop in the cyclone is not as required, then you can have feed particles short circuiting to the overflow, which means coarse particles are going to the overflow, and that will bring an error. So ideally, you want to minimize these values here to have an efficiently performing hydrocyclone, or for quality control purposes, you can work out imperfection, and based on the value of the imperfection, you can keep an eye on the daily performance of a cyclone as well. And constructing efficiency versus, for example, reduced performance curves can give you a comparison of different types of cyclones or different operations at different particle size distribution. And based on the shape of the cyclone, you can actually tell whether the cyclone is working at an efficient rate or not. So this can be done in typical plant, by having a standard and comparing it with a standard on daily basis or on weekly basis to see how it performs. Again, here, what I want you to understand is also you have a hydrocyclone, but how does, for example, changing the variables affect the cut size of a cyclone? Okay, if you increase pulp density, what happens? Everything else obviously is kept constant, but if you change, if you want to experiment with the hydrocyclone, you want to optimize it and so on, there are things that you can change. So probably when you buy it, you already have fixed things. For example, the inlet diameter is already fixed. The size of the cyclone is probably already fixed. The outlet is already fixed. Maybe you can't change those, but you can play with some things to optimize it. So you can change density. You can, for example, play with operating pressure, flow rates, and so on to optimize it. But at least you need to know the consequence of what happens when you do those. Okay, so for example, if you change pulp density, increase pulp density, typically you increase percent solids and you increase viscosity. So in this case, instead of working, say, at 60% solid feed, you may want to work at 70% or 75% solids. Maybe you just want to increase the capacity of the cyclone, but you need to know what you expect to happen then. So for example, with that, you would significantly reduce the sharpness of the cyclone because you're feeding lots of material to the cyclone. What you expect is probably some of the particles will go to the overflow to the fine portion. So you increase cut size and you would probably have a pressure drop inside the cyclone as a result. Okay, so you can do the same for all the others. So for example, you have vortex finder. You can have vortex finder is the overflow. Okay, so again, if I make that bigger, I'm allowing more particles to go to the overflow. So with that, I'm allowing feed particles to go to the overflow, and that will increase the cut size. And if I increase pressure, with pressure, I increase internal pressure. So increasing pressure should lead to decrease in cut size and so on. So try to get your head around it and try to understand why these variables have these effects on the cyclone performance. But it comes down to, if you want to understand this, it comes down to what happens to the internal pressure inside the cyclone by varying something. Okay, if I make the cyclone bigger for same feed rate, same everything, I am reducing the internal pressure. Okay, right? So when I reduce internal pressure, I would increase the cut size because I allow more coarse particles to go to the overflow. So something like that. So at least try to have that basic understanding of how a cyclone works so that you can at least predict what happens when you change some variables. Okay. I think that is it for today. So I guess what I'm trying to do is not necessarily telling you what comes on the exam if you guys are curious, but it's more to do with what at least I expect you to learn from this course. And if you can, understand some of these things, understand how you can do some of the problems in your tutorial and so on, you should be able to do the exam anyway. So I don't think that's a problem. Okay, but at least these are some of the focus areas that you can use as a guide to prepare yourself for the exam and maybe to take some things from this course as well. Okay. So I think you guys can ask any questions regarding, anything about this course, what we have gone through so far, and any other things that you want to raise. I think you should be free to raise it, really. So ኤልያስ የአሳይመንቱን ምንድን ነው ዲው ዴት እንዲጨመር ጠይቀኸኛል። አይ ቲንክ ኖ ፕሮብለም ከፈለጋችሁ። አይ ቲንክ የኤግዛሙም ስኬጁል ተራዝሟል። ስለዚህ ችግር የለውም መጨመር ትችላላችሁ የፈለጋችሁትን እንዳልከው።
የሁሉም ጥያቄ ነው ለሰኞ ቢሆንልን።
ያ ኦል ጉድ ሌላ ጥያቄ ያላችሁ? ሌላ ማንሳት የምትፈልጉት ነገር? ስለዚህ ግሩፕ ኦልሬዲ ክሬት አደረጋችሁ ለሪፖርት ለላብ ሪፖርት የሚሆን
ለላብ 6 ሆነን ግሩፕ ክሬት አድርገናል። ግን ሃይድሮሳይክሎን መስራት አንችልም፣ ምክንያቱም እንትን የለም።
ኦኬ። ስለዚህ ለዛ የላኩልህን ዳታ መጠቀም ትችላላችሁ። አይ ቲንክ የላኩልህ በላቡ ላይ ባለው ፕሮሲጀር ነው። አይ ቲንክ ኢንፎርሜሽኑ የላኩልህ በቂ ይመስለኛል። የሆነ ሌላም አዲሽናል ኢንፎርሜሽን የምትፈልጉ ከሆነ ሪፖርቱን ለመጻፍ ንገረኝና እልክላችኋለሁ። ግን አይ ቲንክ በቂ ይመስለኛል ያ ኢንፎርሜሽን።
እሺ፣ ክራሽንግ ላይ ግን የጃው ከሰራን አይበቃም? ጃው ክራሽር ነው አሁን ያለው
የሰራችሁት?
አዎ፣ ያለው ላብም ያለው ጃው ክራሽር ነው።
ስለዚህ ፕሮሲጀሩ ላይ ያለውን መስራት አትችሉም ነው ወይስ መስራት ቻላችሁ? እሱ
አይ ትንሽ ያስቸግራል። አሁን ባለፈ ሳምንት ስንሰራ የነበረው ኢፌክት ኦፍ እንትን ጃው ሰፓሬሽን ኦን ክራሽንግ የሚል ነው። በ2 ሚሊ ሜትር እና በ8.5 ሚሊ ሜትር ሰፓሬሽን ሳይዙን እንደዚህ አድርገን ነው የሰራነው።
ኦኬ ያ አይ ቲንክ በጆ ክራሸር ከሰራችሁት ቁጥሩ በጣም ትልቅ ነው የሚሆነው ካልኩሌት የምታደርጉት። አይ ዶንት ኖ ወይ ደግሞ በጣም ትንሽ ቁጥር ካልኩሌት ታደርጉ ትችላላችሁ። እንዴት እንደሰራችሁት አላውቅም። ቪዲዮ ኤኒዌይ አይ ቲንክ ምንም ችግር የለውም። በዛ በሰራችሁት መሰረት ጻፉ ሪፖርቱን። ግን እስቲ ከቻልኩኝ ኤኒዌይ እንዴት እንደሚሰራ ላቡ የሆነ ሪኮርድ አድርጌ ልክላችኋለሁ። አትሊስት እንዲገባችሁ እንዴት ነው የሚሰራው ቦንድ ወርክ ኢንዴክስ የሚለውን እንድታቁት፣ ላብ ውስጥ እንዴት አይነት ፕሮሲጀር ነው የምንከተለው የሚለውን እንድታቁት። እስቲ ቪዲዮ ካገኘው ሪኮርድ አድርጌ ልክላችኋለሁ።
ያው ሲቭ አናላይሲስም እሱም ቀላል ስለሆነ
እሱ ችግር የለውም። ያ ሳምፕሊንጉም ችግር የለውም። አይ ቲንክ
ሳምፕሊንግ እሱን ገና አልሰራነውም፣ ግን ሳምፕሊንግም ለመስራት ብዙ ኢኩዊፕመንት ያላቸው አይመስለኝም።
አይ ሲ
ሪፊሊንግ
ያ አይ ቲንክ አንዳንዱም መተው ትችላላችሁ። ሳምፕሊንግ ላይ ያለውን
ባለው
ሁሉንም ሳምፕሊንግ መስራት ካልቻላችሁ የተወሰነውን እንኳን መስራት ብትችሉ አይዲያው እንዲኖራችሁ አይ ቲንክ ኢትስ ኦኬ። ስለዚህ መቼ ነው የሚያልቀው ሴሚስተሩ?
ሴሚስተሩ ፈተና የምንጀምረው ከማርች 10 ነው ፈተና የምንጀምረው።
ኦኬ።
ስለዚህ በየመካከሉ 3 ቀን ጋፕ ስላለ ሶስት ቀን ጋፕ አለ። 5 ኮርሶች ነው የምንወስደው። ስለዚህ ከ15 ቀን በኋላ ያልቃል። ማርች 5 ያልቃል። እስከ ማርች 5 ድረስ ከማርች 30 ድረስ ያልቅና ቀጣይ ሴሚስተር ይጀምራል።
ኦኬ አይ ቲንክ አይቻለሁ ታይም ቴብሉን። ይሄኛው ወደ መጨረሻ አካባቢ ነው መሰለኝ።
ፋይናል ኤግዛሙ ከስንት ነው ከቨር የሚያደርገው?
መጀመሪያ ያለኝ አይዲያ ከ40 እስከ 50% ነው። ግን እስቲ ምንድን ነው የሚመስላችሁ? ኤግዛም ብዙ ጊዜ ኤግዛም ብዙም እንትን አለ ለእኔ ከኤግዛም ይልቅ ሞር እንደ ፕሮጀክት አይነት እንደዚህ እናንተን እንትን አንደርስታንዲንግ የሚፈልግ ነገር ላይ ብትሰሩ ሞር አይ ቲንክ እመርጣለሁኝ። ምክንያቱም ስራ ላይም ብትሆኑ የምትሰሩት ቁጭ ብላችሁ ምን ታውቃላችሁ ሳይሆን የሆነ አይዲያ ይሰጣችኋል፣ ይህን ስሩ ነው የምትባሉት። ሞር እንደዛ አይነት ነገር ቢሆን ደስ ይለኛል። ግን አይ ቲንክ ለአሁን ኤግዛም አለ 50% 40% somewhere around there ነው፣ በሁለቱ መካከል ነው አይ ቲንክ።
አይ አሁን ሌላ ትምህርቶችን ስናደርግ የነበረው አሁን ይሄን ማስተር ኤምኤስም ስለሆነ ሰሚናሮች እንደዚህ ፕሮጀክቶች ምናምን ነበር ስንሰራ የነበረው ማለት ነው። ሌሎች ትምህርቶች ላይ ስፔሻሊ ከ40 ከ50 የሰራናቸው ሰሚናሮችን ፕሮጀክቶችም አሉ። ከ30 ከ40 ነው ከቨር እያደረጉልን ያለው ፋይናሉን ማለት ነው። ምክንያቱም ፕራክቲካል ላይ ኮንሰፕት ማድረግ አለባችሁ ስላሉ እና ማወቅ ያለባችሁን የፕራክቲካል ነገሮች ሰርታችሁ ማለት አለባችሁ ብለው ስለሚያስቡ ለዛ ነው እየሰጡን ያለው።
ስለዚህ ላብ ሪፖርቱ ላይ ብዙ ጊዜ ብታባክኑ ጥሩ ነው። ለሱ ብዙ ወይት እንስተው
እንደዛ ብናባክን ጥሩ ነው ብለን እናስባለን። ምክንያቱም ማወቅም አለብን፣ እዛም ያሉትን በደንብ ሰርተን እንትን ማለት አለብን። ስለዚህ በቻልነው መጠን ላቡ ላይ ብናባክን ኤግዛምም አንድ ሳምንት ያራዘምነው እኛ ነን ትናንትና ላብ ለመስራት አንድ ሳምንት ያስጨመርነው።
ስለዚህ አይ ቲንክ ባለፈው በነገርኳችሁ መሰረት ላቡ 20% ነው፣ አሳይመንት 40%፣ ኤግዛም 40% ብለን ነው ያዝነው። አይ ቲንክ እንደዛ ነው ያዝነው። ስለዚህ የላቡን ወደ 30 መውሰድ እንችላለን ሁሉም ሰው የሚስማማ ከሆነ። ከዛ ኤግዛሙን 30% ማድረግ እንችላለን።
እንደዛ ብናደርገው
ሁሉም ሰው ይስማማዋል እንደዛ?
ያስማማል።
ኦልራይት። ስለዚህ ኤግዛሙ 30% ማለት ነው። እሺ
ኦኬ።
ስለዚህ ከሁሉም ቻፕተሮች ነው ከቨር የሚሆነው አይደል?
ያ ከሁሉም ቻፕተሮች ነው። ያው ብዙ ጊዜ እንዴት ነው ለራይቲንግ ሪፖርት ራይቲንግ እንድትለማመዱ ነው ዋናው የላብ ሪፖርቱ። አሳይመንቱ ዋናው ሪሰርች ስኪል እንድትለምዱ ነው። የሆነ ኢንፎርሜሽን በሌለ ኢንፎርሜሽን እንዴት ብላችሁ ነው ኢንፎርሜሽን አፈላልጋችሁ አይዲያችሁን አንድ አይነት አድርጋችሁ የምትጽፉት የሚለው ነው። ሞር ሪሰርች ስኪላችሁንም በዛውም ትጨምራላችሁ። ኤግዛሙ ግን ፕሮብለም ሶልቪንግ ነው። ስለዚህ ሞር የቱቶሪያል ላይ የምንሰራው መጨረሻ ላይ የምንሰራው አይነት ኤክሰርሳይዝ አለ። ሞር እንደዛ አይነት ነገር ነው የሚሆነው። ስለዚህ ከሁሉም ቦታ አሁን ዛሬ ሜንሽን ያደረኳቸውን ሁሉንም ነገሮች የሰራናቸው ከዛ ጋር የተያያዙትን የሰራናቸውን ኤክሰርሳይሶች ለማንበብ ሞክሩ። ብዙም እንትን ላይ አታተኩሩ። የሆነ አሁን ለምሳሌ አንዳንዴ ጆ ክረሸር ኦፕቲመሙ በዚህ ሬንጅ ነው በዚህ ምናምን ሚል ሜንሽን አድርጌ ሊሆን ይችላል። ኢቭን ስለ ቦል ሚል ስለ ሳግ ሚል ሳወራ ይሄን ኦፕቲመም ሬንጁ ብዬ ሊሆን ይችላል። እሱን እንድታውቁ አልጠብቅም። አሁን ማለት አይጠበቅባችሁም። ቁጥሮቹ ከዚህ እስከዚህ ናቸው ምናምን የሚለውን እንድታውቁ ኤክስፔክት አላደርግም። ግን ሞር ኮንሰፕቶቹ ላይ እና እንደዚህ ፕሮብለም ሶልቪንግ ላይ ነው የሚያተኩረው። ኦኬ።
ሌላ እንትን ላይ ደግሞ ኤግዛሙን እንዴት ነው ለእናንተ የሚደርሰው? አሁን ኦንላይን ነው እንትን የምንለው ወይስ?
አይ ቲንክ ጥያቄ አዘጋጅቼ መላክ እችላለሁ። ከዛ እነሱ ፕሪንት አድርገው መፈተን ይችላሉ። አላወራውም ብዙም ስለሱ ከነ አቡበክር ጋር፣ ግን ሞስት ላይክሊ ሊሆን የሚችለው ጥያቄ ልኬላቸው ለእናንተ ፕሪንት አድርገው መፈተን ነው ሞስት ላይክሊ የሚሆነው።
እስካን ተደርጎ ለእናንተ ሊደርስ ነው።
ከዛ በኋላ ያው እንዴት አይ ቲንክ ማረሙ ላይ ሰው አዘጋጁ ብያቸው ነበረ። ግን ደግሞ አንዳንዴ ማየት ፈልጋለሁ ያረመው ሰው ማን እንደሆነ እንዴት እንዳረመው ማየት ፈልጋለሁ። እኔ ባየው አይ ቲንክ ማየት አለብኝ የሰራችሁትን ነገር። ኤኒዌይ ማንም ማረመው ማንም፣ ግን እሱ ላይ ስካን አድርገው ከላኩልኝ አንድ ነገር ነው። ካልሆነ ደግሞ እስቲ አውል ፋይንድ አውት በምን አይነት መልኩ
እንደዛ ቢሆን ይሻላል። ሌላ ሰው ከሚያርመው እናንተ ያስተማራችሁን ታደርጉ። ስለዚህ እኛ እንደዛ ተዘጋጅተው ተፈትነን መጨረሻ ላይ ስካን አድርገው ለእናንተ ቢደርስ ይሻል ይመስለኛል።
እስቲ እንግዲህ ያኛው አይ ቲንክ ምናልባት የተመረጠው ኦፕሽን እሱ ሊሆን ይችላል። ግን እስቲ ዲስከስ አደርጋለሁ እዛ ምን አይነት ሀሳብ እንዳላችሁ።
ስለዚህ አሳይመንት ሰልን እናስገባለን። ጨርሰናል። እናመሰግናለን።
በቃ መልካም። እሺ ሌላ ነገር ካላችሁ ጥያቄ እንደዚህ በዛ በቴሌግራም ላኩልኝ። አዘዋይስ ጉድ ላክ።
በኢሜይል እናድርገው ወይስ
ለብቻ ካላችሁ ስፔሲፊክ የግላችሁ ከሆነ ኢሜይል አድርጉልኝ። ለሁሉም ሰው ደግሞ ማወቅ ያለበት ጥያቄም ከሆነ በቴሌግራም ብትልኩ አይዋል።
አይ አሳይመንቱን በኢሜይል እንላከው ወደ ፒዲኤፍ እንቀይረው ወርዱን።
አይ ቲንክ አሳይመንቱን አይ ዶንት ኖ እንዴት ነው ለየብቻ የሁሉም ሰው ከሚደርሰኝ አንድ ላይ እነሱ ውስጥ ኮሌክት ማድረግ ከቻሉና በሆነ በአንድ ፎልደር ለኔ ቢልኩልኝ። ለሌሎቹ እንዴት ነው የምታስገቡት? አሁን አሳይመንት ፕሪንት አድርጋችሁ ነው የምታስገቡት?
አይ በኢሜይል ነው። ሶፍት ኮፒ ነው። አሁን ሶፍት ኮፒ እያዘጋጀን ያለ ነው። አሳይመንቶቹንም ላብ ሪፖርቱንም ሶፍት ኮፒ ስለሆነ የምናዘጋጀው ለእናንተ ቀጥታ መድረስ ይችላል። አሳይመንቱና ላብ ሪፖርቱ ላይ ምንም ሁሉንም እናንተ
ስለዚህ ሁሉም ሰው ለየብቻ ከሚልክልኝ አይ ቲንክ ኮሌክት አድርጎ የሁሉንም አንድ ላይ ለምሳሌ ወደ እዛ ላሉት ሰዎች ለስታፍ ሜምበር ሁሉም ሰው ቢያስገባ በኢሜል
በኤልያስ በኩል መላክ እንችላለን። ሪፕሬዘንታቲቭ በኩል
ወይ ደግሞ በኤልያስ በኩል አሰባስባችሁ አንዴ መላክ ትችላለህ ኤልያስ?
እንደዛ ይቻላል።
በቃ እንደዛ አድርግና ሁሉንም አንዴ ላክልኝ። የሁሉንም ተማሪ ከነ አይ ቲንክ በደንብ ከቨር ፔጁ ላይ ስማችሁ ምናምን በስራ ከጻፋችሁ የማይማ እንደሆነ ማየት ስለምችል ችግር የለው።
እንደዛ አድርገን የሁሉንም እንላለን። ሪፖርቱንም እንደዛ እንልክላችኋለን።
ኦኬ እሺ።
የላብ ሪፖርቱ መቼ ነው የሚገባው? የላብ ሪፖርቱ የሚገባበትን ቀን ብነገረን መልካም ነው።
አይ ቲንክ መጀመሪያ መጨረስ አለባችሁ። ከጨረሳችሁ ቢያንስ 2 ሳምንት እንደዚህ ያስፈልጋችኋል ሪፖርቱን ለመጻፍ። ስለዚህ ገና ስላልጨረሳችሁት እንደጨረሳችሁት ኤልያስ ልትነግረኝ ትችላለህ ላቡ?
እንደጨረስነው ጽፍላችኋለሁ ቴሌግራም ላይ እንትንም ላይ ስልካችሁን እንትን ብትሉኝ በእንትንም በዋትስአፕም ማውራት እንችላለን።
እሺ ችግር የለም ልክልሃለሁ።
እሺ እናመሰግናለን።
መልካም እሺ።